Hi, and welcome to the flipped instructional recording for atoms. As we get started, be sure you take notes during the recording. You do want to update those in your science notebook, and remember to update your slide with the lesson number and title. So if you're looking at the science notebook slide, you may not be able to see all of this in the recording. I don't know if it'll let me move it, but you'll update the unit number and the lesson number. This is 2.02 matter, and then your notes and things like that will update as well. All right, so now let's get into the lesson. So we're talking about atoms, and we know that we want to pull up and be ready to get those guiding questions done as well. So we'll focus on those when we get to that page. But we're talking about matter being the substance all around us. Actually, all solids, liquids, and gases you see and touch every day are examples of matter. Scientists study matter to understand exactly what it is at the most basic level. They also continue to study the particles that compose matter. These particles are called atoms. More than 2,000 years ago, the great philosopher Democritus suggested that matter is made up of tiny particles. In the early 1800s, John Dalton stated that matter is made of tiny particles called atoms that are invisible, meaning that atoms can't be broken apart. Indivisible, that word. They're not able to be divided or broken apart. Let's see, I'll scroll down. So in ancient times, before technological advances, some people thought that matter, such as the Acropolis, was made from tiny particles. So here is the template slide. Again, you should open up your existing PowerPoint. You started a slide or a new presentation the last lesson, so you should just be adding to that and not creating a new one each time. You are going to want the key words on the left side in your notes. And then here are the guiding questions that we'll be looking at today. So we'll get these answered as we read through the lesson. If the little chart in there doesn't work for you, remember you can delete that and just type or copy and paste the questions. And that way you can answer them, leave space, however works best for you. All right, so now we're getting into the lesson. And the first question that we're looking at, guiding questions number 1, is what are atoms and why are they important? So early scientific discoveries. We're talking about early scientists and philosophers used logic and observation to answer questions about nature. They believed it was more logical to consider matter as being continuous or unbroken. Scientific methods changed in the early 1800s when scientists started conducting carefully controlled experiments and taking measurements. From studying the way materials combined in chemical reactions, John Dalton concluded that matter was made of small yet invisible particles. He called these extremely small particles atoms. Dalton thought atoms were solid little balls that could not be broken into smaller parts. So in this lesson, you'll learn about the contributions of various scientists to the model of atoms and how history shaped the current model. All right, so if we look at this picture, one thing I encourage you to put in your notes is to draw out, just like we talked about in the last lesson. I would write John Dalton, and I would draw a picture of this in your notes, or if you are pasting images in, you could take a little screenshot, use the snipping tool, and paste that in so you know that this is what John Dalton's model first looked like. So I said in the last lesson, this looks like a ball of cookie dough with chocolate chips and pecans in it, and that is what those particles look like. So this image says, how many atoms are in a drop of water? There are more atoms in a drop of water than there are drops of water in the Great Lakes. All right. So what are atoms and why are they important? Question 1, we've talked about what they are. We know that atoms are basically the building block of of everything, right? They're a tiny particle. It's the fundamental building block of substances. The properties of an atom determine the properties of the element made up of only those atoms. So what that means is if you have an element of carbon, you only have carbon atoms in it. So there's nothing else. So that is the definition and why they are important, because they make up everything. Question 2 is describe Dalton's research, and what did Dalton think atoms were like? So we talked about that on the last slide. We talked about how he figured out what an atom was, and you could describe what he thought they looked like. So now we're getting into talking a little more about elements. So in Dalton's research, Dalton found that substances always combined in the same way. So that's something you could add to number 2. He reasoned this because the atoms of a substance were always the same. He also proposed that some materials were made of only one kind of atom, and he called these materials elements. So number 3 says, what is an element? Here's the definition. It's a type of atom with a particular number of protons in the nucleus. A pure substance with only one type of atom throughout. So carbon atom, the element carbon only has carbon atoms in it. So that's what that means when only one type. An element cannot be divided into smaller parts. Okay, so one element of carbon, if we're talking about an atom of carbon, that's the smallest thing. It cannot be broken down further than that. Today, scientists have discovered more than 100 elements and thus more than 100 types of atoms. Dalton also found that atoms combined in small whole number ratios. For example, 2 hydrogen atoms combined with 1 oxygen atom to form water. Since he found only whole number ratios, he felt that the atom could not be further divided. So that should give you an answer to 1, 2, and 3. So what does Dalton's model of the atom look like? Remember, it's a solid round sphere with like a cue ball. So it's just like a circle. Here, this shows a picture of 2 atoms of hydrogen combined with an oxygen to form a water molecule. So you can see 2 hydrogens and an oxygen. All right, moving on, we're talking about Thomson's atomic model. So over the next century, scientists discovered many elements, but the model of the atom as a solid sphere did not change. Then, in 1897, J.J. Thomson conducted experiments leading him to propose the existence of negatively charged particles inside the atom. He proposed that these particles are part of every atom. Today, these negatively charged particles are called electrons. Okay, so electrons definitions. It's a negatively charged particle, and it has much less mass. If you remember in the last lesson, we looked at sizes, and electrons are much smaller. So again, in your notes, I would draw 1897 or write out J.J. Thomson. And here's a picture of what his model looks like. So question 4 says, how did Thomson's atomic model differ from Dalton's? So if you remember, Dalton's model, it was just a round sphere and everything was in it. Thomson figured out that electrons are there, but they're sticking out, if you notice the blue dots here, on the outside. So you notice there is something different. So based on Thomson's work, the model of the atom changed. The proposed new model of the atom appeared to be a positively charged sphere with negatively charged particles peppered throughout, like raisins in a muffin. Scientists chose to name the model after an English pastry called plum pudding. So it's the plum pudding model. You could put that in your notes as well. And so why did the model of the atom change? We know that advances in technology allow scientists to take a more in-depth look. So we updated the model. So that should get you through number 4. Going on, Rutherford in 1908 adapted our model a little more. So Thomson's plum pudding model had a short life. About 10 years after he proposed it, Ernest Rutherford completed a series of experiments using beams of positively charged particles. He concluded there was a center of positive charge within the atom rather than the atom being an entirely positively charged sphere. Rutherford proposed that the positive charges balanced the negative charges of the electrons. He called these positive charges protons. Rutherford concluded that atoms contained one proton for each electron. A proton is much more massive than an electron, but electrons and protons have equal yet opposite charges. He believed electrons circled the region of tightly packed protons, called the nucleus, and the rest of the atom was simply empty space. All right, so a couple of questions here. How are protons and electrons different in charge? We know that protons are positive and electrons are negative. How are protons and electrons different in location? We know that protons are located in the nucleus and electrons are located outside the nucleus of the atom. And the last question, how are protons and electrons different in mass? We know that protons are much more massive than electrons. So if you click this, how big? If an atom were as big as a football field, the nucleus would be the size of a baseball in the field. So think about that. All right, so something to update in your notes. You've got Ernest Rutherford, 1908. Here's the updated model. You've got a nucleus with electrons in an outer shell that are, we don't know that they're orbiting yet. We just know that they float around. We don't know that they have a pattern or anything. So we can answer 5, how did Rutherford's atomic model differ? We know that the electrons now had a little more definition in them there, so you can update that. And then here's a little game that you can play. Dalton, Thomson, and Rutherford each made important contributions to the current understanding of the atom. But what did each scientist discover? Do you think you can separate one scientist's discoveries from the other? So this will be a great game for you to go back through and just see if you're able to distinguish between those scientists' discoveries. All right, so now the discovery of a neutron. One problem with Rutherford's model was that the total mass of protons only accounted for about half of the mass of an atom. Rutherford consequently proposed that there must be other particles in the nucleus possessing no charge. He was right. In the 1930s, scientists discovered this particle and called it the neutron. Neutrons have about the same mass as protons. The number of neutrons in the nucleus is about the same as the number of protons. It is not exactly the same, but the numbers are not always equal. So now the mass, charge, and location of the 3 most important particles that make up an atom were known. So what is the charge of a neutron? We know it is no charge. It's neutral, just like the beginning of the word neutron. How does the mass of a neutron compare to a proton and an electron? So we know that they're about equal to protons, about the same size, but they are more massive than an electron. All right, so here's an image giving you an idea of protons and neutrons together to form a nucleus and your electrons that are on the outside. Okay, parts of the atom. So here is an activity that you can do to go through and test your knowledge of some of these terms that we have talked about so far. The electron in an atom. So number 6, you could now answer it on the guiding questions. What led scientists to the discovery of the neutron? You can now answer that. And now we're looking at number 7. How do protons, neutrons, and electrons differ? Actually, you can answer that from the last slide as well. So that answer's on page 7. And number 8, what does the current atomic model look like? Okay, so the current model, known as the quantum mechanical model, also possesses proposes electrons having certain particular energies, but their exact positions are not known. The only thing that is known about an electron's position is that it's likely to be found in various regions of space around the nucleus. So how is the current model of the atom different than Bohr's proposed model? So the model of the atom has changed. If you look, you should have this kind of timeline in your notes. And we know that the Bohr model believed electrons traveled specific paths around the nucleus, and the quantum mechanical model proposes that the exact location of the electron is not known. Instead, scientists propose a specific region outside the nucleus where the electron is likely to be found. All right, so if you look through, this just gives you an idea. It says this is a statistical probability of the location of electron in orbit. All right, so particles in an atom. This is an activity to just help you figure out and kind of organize the information you know about protons, electrons, and neutrons. And the current model. Whether electrons were stationary or moving was still a puzzle. Rutherford thought electrons circled the nucleus in much the same way that planets revolved around the sun. This is called the planetary model, and although it's about 100 years out of date, that's what most people think an atom looks like. Niels Bohr's later model shows electrons traveling only in particular paths with certain defined energies and with no energies in between. So that gives you the answer to number 8. All right, so wrapping up the lesson, let's check what we learned. You can answer the following. We know that Dalton's model, we know what that looked like. J.J. Thomson's was next, then Rutherford, and now the current model. So make sure you have an understanding of that in your notes. And the next steps for you would be to look for a flip follow-up session and attend Help Lab if you need any extra support. Have a great day.